So before we can measure SEM, and there's going to be different ways of measuring it. This is going to touch on that first way. Okay, so if we go by that slide before, and we're talking about it's measured from a sampling distribution. Well, obviously, you first have to understand what is a sampling distribution. And so the definition is here. It is a frequency distribution for a sample statistic, an estimate, right? That is obtained through exhaustive sampling. So what do we know from this? Well, we know that we are going to be exhaustive sampling. And that was discussed when we talked about Z-scores, right? We talked about, no, I'm sorry, let me back up. It wasn't talking about Z-scores. It was when we talked about X-bar being an unbiased statistic. So in order to show that X-bar is an unbiased statistic, what you had to do is exhaustively sample. And once you did that, you found that half the time X-bar overestimated mu. The other half the time it underestimated mu. And if you averaged out all your X-bars, you were left with mu, whatever mu was. The over and the under canceled out, and you were left with the parameter, okay, in this case mu. So to exhaustively sample, you learn that what you have to do is you decide on a sample size. Let's say it's 10, 20, 30, whatever. Decide on a sample size. And then you go to your population and you take a sample from the population. So if you decide you're going to use sample sizes of 20, fine. You go to your population and you take out a sample of 20 scores. And then you calculate X-bar. Then you go back to the population and you get another 20 scores, right? Now remember, the point of exhaustive sampling is you keep doing that until you have all possible combinations of numbers in your samples. You can't have any duplicate samples. And remember that, let's say, I'm not going to go through a sample size of 30 here, but let's say your sample size is 3. You can have the numbers, 1, 2, 3. Let's say that's a particular sample. 3, 2, 1, you wouldn't count as a separate sample. It is a duplicate. Remember, the order of the numbers doesn't matter. Okay, so that was just a quick refresher on exhaustive sampling. If you need to, you could just go back and read up on that or listen to the lecture, but make sure you understand exhaustive sampling. Okay, so what we're going to do is we're going to exhaustively sample, and then we're going to calculate something on every sample. It could be X-bar, and then we just plot all the X-bars from exhaustive sampling. It could be standard deviation. It could be S. Then we plot all the S's that we calculated through exhaustive sampling, or variances, S squared. But the key is that you're plotting not raw scores, you're plotting estimates, a sample statistic. So we are going to go back and review the different distributions. All right. We're going to then focus our attention on the sampling distribution of a particular estimate. We're going to be focusing on the mean of samples, okay, the mean of every sample. And that's called a sampling distribution of the mean. All right, so let's just review population. All right, if you have a population, well, this is obviously not a real population because look how perfect it is. Normally distributed, but it's hypothetical, this discussion. All right, so let's say you have this population. What you would plot on the x-axis are all the raw scores, right? So if this is IQ or weight or extroversion or optimism, whatever this is, you plot everybody's score in the entire population, and then the mean of all these scores is mu. And if we wanted to, we could calculate the average distance these scores are to the mean, right? How would you do that? Well, you'd have to calculate, first, you'd calculate variance, the variance for this population. And then you would take the square root of variance to get standard deviation. And then standard deviation is just the average distance scores are to the mean. All right, so it would be looking at the average distance, x is to mu. All right, so if all of these scores here are grouped really, really close together around mu, then we're going to get a standard deviation that is small. But if these x bars are way spread out from one another, that means the average distance scores are to the mean is larger, and our standard deviation will be larger. Okay, now if we look at a sample, basically the only difference is instead of plotting all the scores in the population, we're just plotting some of them, right? Because we only have a sample, so these are all the scores in the sample. The mean of the sample is x bar, and if we wanted to, we could measure the variability of this distribution, and again, we could use standard deviation. Standard deviation would be the average distance, right? So the average distance that x is to x bar. We wouldn't use mu because mu is if you have a population. We use x bar if you have a sample. So here the standard deviation is the average distance x is to x bar. And again, if all these x's are clustered or clumped together, then the average distance x is to x bar is going to be small. But if these if these x's are all spread out, a lot of dispersion, then the average distance x is to x bar is going to be much greater. Okay? Now let's talk about the sampling distribution. Now remember, we're going to calculate the sampling distribution of the mean. It doesn't have to be. You could do the sampling distribution of standard deviations or variances, but we never do that. All right, we're going to focus on what we do in the real world, and that is we look at the sampling distribution of the mean. First off, you have to start with a population. And I don't know how this population is. Could be 100, could be 1,000,000. Whatever size it is, you have to decide on a sample size, because what you're going to do is you're going to exhaustively sample from this population. So whatever this is, could be 50, 5,000, I don't know, but make sure it doesn't change, right? You have to keep whatever sample size you decide on, that's the one you have to stick with. All right, so once you have your sample, the next step is to calculate x bar from that sample. All right, and then the next step is to take this x bar and plot it. All right, you're going to be plotting more than one. You're going to just keep a running tally here. You're going to just plot every x bar that you calculate. How many are you going to calculate? Well, it depends how many samples you need to take. How many samples do you need to take? Well, you have to exhaustively sample. So you're going to keep going back to the population, taking a sample, calculating x bar, and plotting it. Okay, go back to the population, get another sample, calculate another x bar, and plot it. And you keep doing that until you have exhaustively sampled. Once you've exhaustively sampled, all right, so once you've exhaustively sampled and you have this distribution, this is called the sampling distribution of the mean. Okay? Now, you might be wondering, why do I have mu x bar here? Well, this is, remember, mu is the mean of the means. This little x bar is just telling you or reminding you that it's the mean of x bars. These are not scores on the x-axis. Remember, you're plotting x bars, you're plotting sample means. So this is a little reminder, all right? But the reason why we're putting mu here, two reasons. One, it's hypothetical, right? Remember what I said when you talk about hypothetical distributions, we use parameters. But the other reason is you have plotted all the means possible through exhaustive sampling. These are all the means possible. That means that's a population, right? You've got them all. So that's why we put mu. Now, one other thing that's important to note is that we could measure how the variability of these estimates, right? Just like we measured the variability of x's, we can measure the variability of means. These x bars, these are just numbers. So how would we do that? Just like we did for a population or a sample. We calculate the standard deviation of these numbers. And so once we calculate the standard deviation of these numbers, that tells us the average distance that that means are to the population mean, right? Mu sub x bar. So again, if we calculate the standard deviation of this distribution, it is the average distance x bar is to mu sub x bar. Okay, we call that sub for a subscript, sub x bar. That standard deviation of the sampling distribution, so once we calculate the standard deviation here, guess what you've just calculated? SEM, standard error of the mean. All right, and the symbol for that is this, SEM, standard error of the mean. When you calculate the standard deviation of a sampling distribution, using this exhaustive sampling method, you have calculated a parameter. You've calculated standard deviation of a population of x bars, right? So we're going to use the parameter. Sigma is standard deviation, and the sub x bar is reminding us that this is the standard deviation of a population of means, of x bars, all right? So if all these x bars are very, very close to one another, like that expensive scale we talked about where all your weights were very, very close, that means there's not a lot of variability. The average distance scores R to the mean is going to be very small. So SEM will be small. But if these x bars are scattered all over the place, if they don't agree with one another and there's a lot of dispersion, that means that the average distance x bar is to the mean will be much greater. SEM is going to be greater because all that SEM is it's a standard deviation. It's just the standard deviation of this distribution. Now, one more important thing, all right, to note. Mu sub x bar is actually going to be equal to mu. The mean of all your sample means equals the mean of the population. We also learned about that when we learned that x bar is an unbiased estimate. Remember that when we exhaustively sampled and we got x bars, we said half of them are going to be below the mean and half are going to be above. And when we average them all out, when we calculate the mean of all these x bars, in other words, mu sub x bar, this is going to just be equal to mu, the mean of the population. That's also very important. I would write that down, okay? So the mean of all these means is simply going to be the mean of the population, mu. Okay, now we've learned that the standard deviation of all your x bars when you exhaustively sample, okay, so the standard deviation of the x bars, that is the standard deviation for the sampling distribution of the mean. It is SEM, all right? SEM is the average distance x bar is to mu. I'm going to keep referring this as to this as x bar for two reasons. I want to reinforce that this is the same thing as x bar. I think some of you are still maybe not quite there yet and remembering that particular fact. So the other reason is it's really cumbersome to say the capital italicized mean, and it's also cumbersome to keep saying this mean of the sample, all right? So I'm just going to say x bar. So SEM is the average distance x bar is to mu after you have exhaustively sampled, right? If you've got this, that means you've exhaustively sampled and you're calculating the standard deviation of all your x bars, all right? So if the variability of the x bars is small. In other words, they're all clustered together. They're all kind of saying the same thing. They're all around the same value. This means the average distance, x bar to mu, is small. On average, the sample mean will be close to the population mean. This means that your SEM will be small. Your measurement of sampling error will be small. And if that's the case, then what you could say is that your x bar is probably a good estimate of mu. Now notice how I stressed this word. X bar is probably a good estimate of mu. We don't know for sure because in real life, you're only calculating one mean for each of your samples, right? If you take a sample of men and a sample of women, you've got one sample mean for the men and one for the women. So your particular sample mean, you won't know if that is good or bad. I mean, close to mu or far away from mu. Once you calculate SEM, all you know is on average how close x bar is to mu. You won't know about your particular x bar. Okay, now, the variability of your x bars is large. Remember, that means that they're all spread out. They're not agreeing with one another. Okay, so if that's the case, then the average distance x bar is to mu will be large. On average, they're far away. This means that your sampling error measured by SEM will be large. All right, the standard deviation of the sampling distribution, because this is what it is, the standard deviation of the sampling distribution will be very large. Large standard deviations mean that x bar is probably a poor estimate of mu. So it's possible that your x bar could be very, very good and very close to mu. But on average, if the SEM is large, that means on average x bars are far from you. You won't know about your particular x bar, but you should go with the odds and say, well, on average, x bar is far away from you, so my best guess is that my mean is also far away from you. Now, this concept is, maybe causing you a little bit of grief and a little bit of a headache or whatever, don't give up. Just rewind and listen to this again. Sometimes the first time you hear it, it is a little confusing. Read the book, do the practice problems, and get in touch with me if it's still not making sense, of course. All right. But little by little, the more you expose yourself to this material, the easier it's going to be for you. All right, now, we've learned ways of measuring sampling error, right? One was just to do x bar minus mu. And we said that is, out of the question. It's stupid because we don't know mu. And if we did know mu, why would we calculate x bar? Well, then we learned, there's another way of measuring sampling error. We just get this distribution, sampling distribution of the mean, and then calculate the standard deviation of that distribution. But there's some things that are pretty stupid about this method too. Number one, you really want to exhaustively sample. If you have a population of 5 or 10, then it's doable. But wait a second. If your population was only 5 or 10 scores in the population, why wouldn't you just go and get everybody's score and calculate mu, right? Why would you be estimating x bar if that were the case? But, again, 99.9999 times out of 10, our populations are huge. And to exhaustively sample would take you probably 100 lifetimes. All right, it's just not something that you can do. We can get a computer to do it, just theoretically, plug in some numbers and say, go at it. But that's not real life. That's not actually getting actual scores in the population. So exhaustive sampling is not something we want to do. So, method 2, that kind of rules that out. Again, it's because it would take you 100 lifetimes depending on how big your population is. Now, let's just pretend that we did. All right, so we lived to be 3,000 years old and we exhaustively sampled from the population. Well, once you exhaustively sample and you calculate the mean of the means, we now know mu. If you know mu, you no longer need to calculate sampling error. All right, because now you know mu. You don't need to estimate it anymore. Remember, the only time we care about sampling error is when we sample and we calculate an estimate from that sample, like X bar. But if through exhaustive sampling we now have mu, that makes sampling error obsolete. We don't need to know it anymore. All right, so it's kind of like, okay, this is stupid for 2 reasons. Oh, now what? Well, there's got to be a solution, right? Because I wouldn't put you through all this unless there was an answer. So let's look at method number 3.